The lunar surface is a graveyard of silence. It is a monochrome expanse where the footsteps of 12 men remain frozen in the regolith, undisturbed for decades. It is a world of magnificent desolation, as Buzz Aldrin famously described it. But do not let the silence fool you. This is also a world of extreme violence. The moon's surface is a shooting gallery for micrometeoroids, traveling at bullet-like speeds. It is a radiation trap, bathed in the lethal ultraviolet glare of the sun and the insidious, piercing energy of galactic cosmic rays. Temperatures swing wildly, boiling water instantly in the sunlight and freezing nitrogen in the shadow. To live on the moon, to truly inhabit it rather than just visit, we cannot remain on the surface. We must go where the moon itself has prepared a sanctuary for us. We must go down. Beneath the gray dust and the cratered plains lies a secret world. It is a labyrinth of subterranean voids known as lava tubes. These are not the cramped, damp caves we are familiar with on Earth. These are basalt cathedrals, colossal tunnels forged in fire billions of years ago. Some are wide enough to house the Empire State Building or swallow the entirety of Central Park. In these deep, silent arteries of the moon, the temperature is a steady, mild -20 degrees Celsius. The deadly radiation is blocked by thick roofs of rock. The micrometeoroids burn up or shatter harmlessly hundreds of meters above. This is the story of humanity's future in the lunar underworld. It is a vision of subterranean space cities, where the next great leap for our species will not be a footprint on the dust, but a light switched on in the dark. To understand why the future of space colonization lies underground, we must first understand the violent geological past of our satellite. Billions of years ago, the moon was a geologically active world. Rivers of low-viscosity basaltic lava, far hotter and more fluid than the lavas we see in Hawaii today, flowed across the lunar Maria. As these rivers flowed, the surface cooled and crusted over, forming a hard roof while the molten rock beneath continued to surge. When the eruption finally ceased and the lava drained away, it left behind hollow conduits. These are the lava tubes. On Earth, gravity pulls hard on these structures. A terrestrial lava tube is considered large if it is 30 meters wide. But on the moon, where gravity is only 1/6 that of Earth, the physics of rock mechanics changes dramatically. The roof of a lunar lava tube can span kilometers without collapsing. Data from the Grail mission, the Gravity Recovery and Interior Laboratory, and the Lunar Reconnaissance Orbiter have confirmed the existence of these massive voids. Gravitational anomalies suggest mass deficits, or empty spaces, beneath the surface that align with sinuous rills, which are the collapsed trenches of ancient lava flows. But the most striking evidence comes in the form of skylights. In the Marias Hills region, a volcanic province on the Oceanus Procellarum, a dark pit gapes open in the sunlight. It is roughly 65 meters in diameter and drops 80 meters straight down before opening up into a void. This is not a crater formed by an impact. It is a roof collapse, a natural doorway into the underworld. The Japanese orbiter Kaguya and NASA's LRO have imaged this and other skylights, including one in Mare Tranquillitatis, the Sea of Tranquility. These are the entry points to a ready-made infrastructure that would cost trillions of dollars and centuries of time to build from scratch. The sheer scale of these tubes is difficult to comprehend. Theoretical models suggest stable lunar tubes could be up to 5 kilometers wide. Inside, the ceiling could soar hundreds of meters overhead. In such a space, you would not feel like a cave dweller. You would feel like you were standing in a vast, dark valley. The volume of a single segment of the Marias Hills tube could contain the entire city center of Philadelphia. It is here, in this unlimited volume, that we will build. Let's address the surface problem and why we cannot simply stay above. The romantic image of a lunar base is often a cluster of domed habitats on the surface, glowing warmly against the black sky, with Earth hanging like a blue marble overhead. This image, while inspiring, is an engineering nightmare. First, there is the radiation sieve. The Earth is protected by a thick atmosphere and a powerful magnetosphere that deflects solar wind and cosmic rays. The moon has neither. On the surface, an astronaut is exposed to solar particle events, sudden bursts of protons from solar flares that can cause acute radiation sickness and death within hours. Even on quiet days, the background galactic cosmic rays, heavy, high-energy ions from exploding stars, gradually shred DNA, increasing cancer risk and causing cognitive decline. To protect a surface habitat, we would need to pile meters of regolith on top of our domes, effectively burying them anyway. Then there is the thermal sawtooth. The lunar day lasts 14 Earth days, followed by 14 Earth days of night. At the equator, daytime temperatures hit a searing 120 degrees Celsius, hot enough to boil water. At night, they plunge to -130 degrees. This thermal cycling wreaks havoc on materials. Metals expand and contract, seals degrade, and electronics fail. A surface base requires heavy, energy-hungry active thermal control systems to keep the humans inside alive. Furthermore, there is the micrometeoroid rain. The Earth burns up meteors in the mesosphere. On the Moon, a grain of sand traveling at 20 kilometers per second hits the surface with the force of a hand grenade. A surface habitat is constantly being sandblasted by these invisible bullets. A larger strike could depressurize a dome instantly. Finally, there is the dust. Lunar regolith is not like beach sand. It is jagged, electrostatically charged shards of glass, created by billions of years of impacts. It sticks to everything, clogs machinery, destroys seals, and shreds lungs if inhaled. On the surface, dust levitation caused by electrostatic charging at the terminators coats everything in a fine, abrasive powder. Inside a lava tube, however, all these problems vanish. The hundreds of meters of basalt overhead provide shielding superior to Earth's atmosphere. Radiation levels inside a tube are negligible. Down there, the sun never rises and never sets. The temperature remains a constant, stable, -20 degrees Celsius. While cold, this is easily managed. It is a stable thermal sink, meaning we only need to generate a little heat, not constantly fight massive fluctuations. The roof takes the hits from micrometeoroids, keeping the city below safe. And while the floor of the tube is dusty, it is dead dust, undisturbed by the solar wind's electrostatic charging. Once paved or covered, it stays down. So how do we enter the abyss? The engineering of access is the first challenge. The skylights are vertical shafts dropping into the darkness. We cannot simply land a rocket inside the hole. The precision required is too high, and the exhaust plume would turn the tube into a shrapnel storm of kicked-up rocks. Phase 1 belongs to the Scouts. Before humans arrive, robots will claim the dark. The European Space Agency has conceptualized the Delos mission, a sphere-shaped robot lowered on a tether. Equipped with LiDAR and stereoscopic cameras, it will hang in the void, mapping the interior in 3D. Other concepts involve cave hoppers, small robots that use the low gravity to hop around the debris pile on the tube floor, and Spherex drones that use cold gas thrusters to fly through the vacuum. These Scouts will look for structural stability. They will check for roof blocks, massive slabs that might have fallen from the ceiling. They will map the floor, which is likely covered in a chaotic pile of rubble, directly under the skylight, known as the talus slope, but may smooth out into a flat floor of solidified lava further in. Most importantly, they will hunt for ice. In the permanent darkness of these tubes, water ice from ancient comet impacts might be preserved, trapped in the cold. Phase 2 is the sky crane. Once a site is selected, the access tower is built on the surface rim of the skylight. This structure will be the lifeline of the city. It will feature a massive solar array farm spreading out across the surface to catch the sunlight, and a nuclear fission reactor for the long lunar night. A heavy lift crane or elevator system will be installed over the pit. In the low gravity, cables can be thinner yet carry more weight. This elevator will lower the first construction rovers, the habitats, and the humans. It is the umbilical cord connecting the sunlit world of power and communications to the dark world of habitation. Phase 3 involves sealing the breach. We do not need to pressurize the entire 50-kilometer tube immediately. That is a task for the 22nd century. The initial approach is the ship-in-a-bottle concept. We will lower inflatable habitats, huge Kevlar and Vectron balloons similar to the beam module currently on the ISS but much larger, and inflate them inside the tube. However, a more ambitious concept is the plug. Engineers could seal the skylight itself. By spanning the hole with a high-tensile membrane or a dome printed from surface regolith, we can turn the area directly under the skylight into a pressurized atrium. The Project Loop concept envisions a 3D printed ring at the entrance, acting as an airlock and interface, while the city grows outward into the tunnel. Now, imagine the architecture of the deep. What does a city in a lava tube look like? It does not look like a sci-fi bunker with claustrophobic metal corridors. It looks like a park. Because the tube protects against the vacuum and radiation, the structures inside don't need to be armored tanks. They can be light, airy, and architectural. We will have inflatable districts, rows of translucent, glowing cylinders resting on the tube floor. Inside, the air pressure holds the shape. Because the external environment is a vacuum, the walls are under tension, and high-strength fabrics allow for large open spaces. We will use regolith shells for shielding on the surface, but inside we might use regolith concrete, or lunarcrete, for flooring, roads, and internal radiation shielding for nuclear power sources. Swarms of autonomous 3D printers will chew up the loose rocks on the floor, mix them with a binding agent like sulfur or a polymer brought from Earth, and print the foundations of the city. We will embrace verticality. The ceiling might be 100 meters high. In 1/6 gravity you can build tall, slender towers that would collapse on Earth. You can have suspension bridges spanning the width of the tube, with gossamer thin cables. Staircases can be steep and spiraling, as climbing them is effortless. To counter the psychological weight of living underground, we will create an artificial sky. The basalt roof overhead can be utilized to project a live feed of the Earth and the stars, or simulate a blue sky with moving clouds, using OLED panels or laser projection. This circadian lighting is crucial. It will brighten to a brilliant blue-white in the morning and soften to a warm amber in the evening. maintaining the 24-hour cycle of human biology, despite the 28-day lunar cycle outside. In a closed system, nothing is wasted. The city must be a biological machine. The air must be scrubbed of carbon dioxide exhaled by colonists. In the early days, this is done chemically using zeolites. As the city grows, it transitions to bioregeneration. Algae tanks and hydroponic farms absorb CO2 and release oxygen. The sheer volume of the lava tube offers a buffer. Unlike a small capsule where air goes bad in hours, the massive volume of a sealed tube section provides a reservoir of air that stabilizes the system. Water is the gold of the moon. We will mine it from the polar craters or from deep ice deposits within the tubes themselves. Once in the system, it loops endlessly. Urine, sweat, and humidity are recaptured, filtered, mineralized, and drunk again. The shower you take today is the coffee you drink tomorrow. You cannot ship steaks from Earth, so the farm becomes essential. The city will have vast hydroponic bays, glowing with pink and purple LED lights, optimized for photosynthesis. They will grow high-calorie crops, sweet potatoes, soybeans, wheat, and leafy greens. Insect protein like crickets and mealworms will likely be the first livestock, as they are efficient, dense in protein, and low waste. Later, tilapia fish farms and even poultry might be introduced. The farm is not just a food source. It is the green lung of the city and a psychological refuge, a place of smell and color in a world of gray rock. A city needs gigawatts to survive. Powering the depths requires a mix of technologies. On the surface above the tube, fields of solar panels will track the sun, but the lunar night is 2 weeks long, and batteries are too heavy to store that much power. Therefore, nuclear power is essential. Small modular reactors, like the kilopower units developed by NASA, will be lowered into the tube or buried near the entrance. Nuclear power is ideal for the moon. It is dense, reliable, and produces heat which is useful in the sub-zero tube. A more futuristic solution involves power beaming. We could utilize the peaks of eternal light at the lunar poles, where the sun never sets. Solar farms there could generate power and beam it via microwaves or lasers to relay satellites, which then beam it down to the rectennas at the skylight of our lava tube city. This creates a planetary power grid. But what is it like to live there? What is the human experience in society in the void? Movement will be delightful. You weigh 16% of your Earth weight. You don't walk, you lope. In the large open spaces of the tube, human flight becomes possible. With a simple pair of fabric wings and a bit of practice, you could strap on wings and fly across the city, powered only by your own muscles. Sports will be reinvented. 3D basketball, zero-G gymnastics, and vertical parkour will be the pastimes of lunar youth. Psychologically, biophilic design is mandatory. We need nature. The architecture will incorporate fractal patterns, natural materials like bamboo grown on site, and running water. The sound of a fountain is not just decoration. It is white noise to mask the hum of ventilation fans and a reminder of Earth. As for governance, who owns the city? The Outer Space Treaty says no nation can claim sovereignty over the moon, but it allows for the use of resources. The city will likely be an international zone, governed by a lunar charter similar to the Antarctic Treaty or the laws of the high seas. It might start as a scientific outpost, run by a commander, but as civilians arrive, miners, engineers, artists, it will evolve into a democracy or a corporate state. Why do we stay? A city cannot survive on subsidies forever. It must pay its way. The economy will be driven by mining, manufacturing, data, and tourism. The regolith contains helium-3, a potential fusion fuel, titanium, and rare earth elements. The tubes provide the base of operations for surface strip mining rovers. The vacuum and low gravity are perfect for creating things impossible on Earth, such as ZBLAN fiber optics, which requires zero gravity to avoid crystallization, perfectly spherical ball bearings, and biological organs printed without collapsing under their own weight. The cold, stable environment and lack of seismic activity make lava tubes perfect for long-term data storage servers. And for the wealthy, the moon is the ultimate destination. The Lava Tube Hotel offers safety that a surface lander cannot. The Grand Hall of the Marius Hills Tube will be the greatest tourist attraction in the solar system. The first cities on Earth were built in river valleys. The first cities on the moon will be built in stone rivers. Subterranean space cities are not just a safety measure. They are an evolutionary necessity. They allow us to shed the spacesuit. Inside the tube, sealed and pressurized, we can walk in shirt sleeves. We can sit in a park and watch a tree grow. We can raise children without fear of solar flares. The lava tubes of the moon are nature's invitation. They are the empty houses waiting for the tenants to arrive. When we finally seal that skylight and fill the great basalt hall with air and light, we will have done more than build a base. We will have birthed a new world, safely tucked beneath the skin of the old one. We will be, finally, Solarians.